समाजात केले माते বাৰু স্যার স্টার্ট কৰিব পাৰে জয়েন কৰিলে ইহঁতে
ওকে
হয়
Anyway, good morning to you all. Let me start with the little bit of radiation zone because I stopped somewhere in between, and that is, although in the screen you see magnetosphere of other solar system planets, but before that I say a few words on the radial diffusion again, because we said that whenever there are disturbances, then our adiabatic invariance gets changed. So it goes to adiabatic and non-adiabatic, and we have shown how the particles can get diffused into different regions. At least the slot region becomes populated with a lot of electrons from the plasmosphere because of the fact that in plasmosphere we have Whistler mode type waves, which we call Hish or chorus. They interact with the particles and they become resonant. It becomes resonant when the frequency seen by the particle is equal to its own zero frequency. So that process gives you kind of pitch angle diffusion, or in other words, that comes about quasi-linear diffusion of the whole system, and quasi-linear diffusion actually redistribute the particles and therefore you go to a kind of different particle distributions. That therefore shows that the particles from the outer zone can go to the inner zone by some kind of diffusion processes. Now, one more process which I have not discussed earlier is the one which is associated with the ultra low frequency waves. That actually gives rise to the particles drift in the direction such that it goes radially downward to the magnetosphere or away from it to towards the tail region. So that process is obtained by like this. Say for example, we have the disturbance in the system in such a way that the first two adiabatic invariants are not disturbed. They remain as a kind of adiabatic invariant. That means particles direct the way it was doing before, and the particles actually bounce as before. Now what is done then? That you disturb the system with the wave, which are ultra low frequency waves, and these waves essentially, since the time period is enough to disturb the system, because the third adiabatic invariant associated with the drift of the particles, and that the drift frequency is given by the drift velocity, and therefore that's very slow motion drift, and therefore you have also a wave which its frequency is very low, and therefore these waves then may have some interactions with the particles or with the waves in such a way that the changes the particle motion. Now in this particular case, the resonance is not the one like the one we described. Here the particle motion is the drift motion, and therefore it is associated with the frequency omega d, we call it. So when the frequency of the wave minus multiple of frequency associated with the drift particles is equal to its own bounce frequency. When that kind of things happens, then the resonance occurs, and resonance essentially means gives rise to a system where it allows exchange of energy between the particles and the waves. So here what it comes is the bound frequency comes. Particle has its own bounce frequency, but you have Doppler shifted frequency because of the wave, and this Doppler shifted frequency is associated with the frequency of the wave plus or minus the frequency associated with the drift of the particles, or in other words, drift frequency. So if the Doppler shifted frequency, that is omega minus some integer with the drift frequency is equal to its own bounce frequency, then we get a resonance, and that resonance gives rise to exchange of energy from the particles to waves. In this particular case, the effect is to change the particle distances from the center of the earth. That means the drift particles will not remain in the same shell. It will go inside the magnetosphere, inside the earth, or it's away from the earth. So when it goes inside the earth, it gets energy because of the fact it is increased magnetic field. When it goes out, it gives you the low energy. So therefore, under this particular system, particles get redistributed in such a way that some particles can get energy, more energy, and they can go nearer to the Earth. So there was a question sometime back that how that these energetic particles can come near to the Earth in the equatorial plane, because it just goes even in the equatorial plane, it goes radially up and down. So it can go near to the Earth in the radial direction, or it can go away from the Earth from the
Hello, sir.
yes.
Your slide is not changing, sir.
Eh?
Slide is not changing, sir. Sir, first slide is only visible.
Oh, okay. Oh, the point is the way I was saying is that that is not in the slide because I'm in the magnetosphere or solar system planets. But the one which I left earlier was I was just talking that without any slide, so maybe I can put it off. But anyway, bear with me at the moment that I am talking about the particles which is radially drifting towards the Earth because of the fact that there is a resonance interaction between the ultra low frequency waves and the particles trapped in the magnetosphere. And that is again a different resonance system, and that resonance system allows particles to go inside the magnetosphere. So even in the equatorial plane, the particle can go from the magnetosphere towards the Earth, and which sometimes suggests that the observationally. Okay, so that's the end of my talk on the radiation belt particles. I go to the one where the magnetosphere of other solar systems. Now, the other solar system planets, as I have shown there are three inner planets, Mercury, Venus, and Mars, and four outer planets, Jupiter, Saturn, Uranus, and Neptune. Out of these inner planets, we see that Mercury has the magnetic field, intrinsic magnetic field. Venus and Mars has atmosphere and ionosphere but no magnetic field. Jupiter, Saturn, Uranus, Neptune, they are the giant magnetosphere with intrinsic magnetic field. Shape, size, and other characteristics will depend upon three properties of or parameters. One is magnetic moment, second is the orientation of spin axis, and the third is the tilt of the magnetic field axis with respect to spin axis. These are the three important parameters which will determine the shape, size, and other characteristics of the magnetosphere. Now let me start with the magnetosphere which has intrinsic magnetosphere planets which has intrinsic magnetic field. In that case, I have to start with Mercury. Mercury, Marina 10 has observed first with their plasma and plasma instrument and magnetometer that these planets have boson and magnetopause. There is magnetic field and charge particle distribution as well. Magnetic moment was seen to be 1 by 3000 that of the Earth. Morphology is dominated by solar-wind interaction. Various characteristics can be obtained by reducing all configurations by a factor of 7 and 7 to 8. Now, for example, magnetopause distance is 1.4 radius of Mercury while that of the Earth is 10 to 11 Earth radii. Now, we can find out the magnetopause distance from the center of the planet by assuming the formula by using the formula that we have already obtained for the distance of magnetopause of the Earth from the center of the Earth. So if you use that formula and if you have the velocity and solar wind velocity and density near the Mercury, then you can obtain the magnetopause distance, and that would be around 1.4 radius of Mercury. But this is small because of the fact that the mu, the magnetic moment of the planet Mercury is small, and therefore the boundary comes nearer to the surface of the planet Mercury, and therefore you get this is the kind of distance that we can have for the Mercury. Now there is nothing very different characteristics here. It is except that it is a very tiny it will be a very tiny magnetosphere because of the fact that the magnetopause distance is such a distance as 1.4 radius of Mercury. So let's see in the second thing. Well, this is shown in the picture. On the right hand side, you see the magnetosphere of Mercury, solar wind coming from the left. It produces Borsuk as before, which could be there because there is a planet, and solar wind is supersonic or supergalvanic, and therefore it will produce a shock, and the same thing, the shock will be a fast shock because the pressure wave that it will meet on the other side would be associated with the either magnetosonic wave or sound wave, which is much small compared to solar wind velocity. And therefore you get a first bow shock, even in the case of Mercury. And the source of plasma is basically the internal planetary source, and in the planet you have a tiny exosphere, and that exosphere can be ionized by the solar wind irradiation like ultraviolet and so on and so forth. So it will produce an ionosphere, and then we can talk about the magnetic reconnection because since it has a magnetic field and then the magnetic field is similar to the orientation is similar to that of the Earth, so it will produce a magnetic reconnection in the front of it, and as before, as in the case of the Earth, the magnetic flux would be brought near toward the tail side, and then there will be tail reconnection, and then that would give rise to convection. And interestingly, both these are observed by the satellite. Now, what are the dissimilarities between the magnetosphere of the Earth and magnetosphere of Mercury? Is that there is no good co-rotation. That may be because of the fact that the plasma, the magnetosphere, is very, very tiny one, and there is no trapped electrons. So there is no radiation belt in this particular case. Again, probably the condition by which the particle gets trapped in the case of magnetosphere of the Earth does not get satisfied here in this case. So there are these two dissimilarities. Then we go back to the outer planets, and the outer planet, first one is Jupiter, and let us discuss something about Jupiter. As you can see, that Jupiter, Saturn, Uranus, Neptune, they are the outer planets. And earlier, when there were not so much of observations, people used to determine the magnetopause distances of different planets by using certain scaling laws. What are the scaling laws? Actually, as if you want to find out the magnetopause distances from the center of the Earth, then you need three, four things. First, the magnetic moment, which is coming at the numerator, mu square, and on the denominator you have rho Vs square. Rho is the density of the solar wind at that point, and Vs is the velocity. Now these are not constant, so they are kind of varies as it moves away from the center of the sun. So the solar wind number density varies 1 by r square. And if you take that the number density at the surface of the sun, surface of the earth is 7, then that constant is replaced by 7, and then you get 7 by r square. It goes on depending upon r, where you are. Now you need develop magnetic field also. So magnetic field radial component has varies as 1 by r square, and azimuthal component varies as 1 by r. This you have seen in the case of the solar wind. So when you discuss the solar wind and then the magnetic field associated with the solar wind, it was shown that the BR, that the radial magnetic field varies as 1 by r square, and azimuthal magnetic field is 1 by r. This is not like that of the Earth. In the case of Earth, it is purely dipole, and there is no azimuthal component of the magnetic field. Anyway, these are the kind of scaling laws. You can go back to the other things. So magnetopause distance and P and the ME are written greater than magnetic moments. No. The magnetic moments of the planet Jupiter is greater than the magnetic moments of the planet Earth. And the and the possible it is possible to obtain the magnetopause distance by using the same formula, where I have seen dP by dE is equal to mP by me to the power 1/3 and r to the power 1/3. This can be obtained. This is very simple because you have to write the expression for dP, that any planet, there you have to write only the magnetic moment of that planet, which is known. Then the rho is the distance, which depends upon 1 by r square. So if you know the um, number density at the Earth, you can find out the density there as writing by 1 by r square. And then velocity. And velocity is almost the same. Solar wind velocity. If you put them there, you can find out dP and d separately. And if you find out the ratio, and ratio is the ratio between the magnetic moment of the planet and magnetic moment of the Earth to the power 1/3 and r to the power 1/3. That is the variation one can see of the magnetic pole distance. So it varies as r, also as the magnetic moment. So the distances of dP can be compared to del dE, which is the magnetic pole distance of the Earth. Next, you can find out the electric field associated with the um, solar wind plasma that is given by V cross V E is equal to minus V cross V by C, and if V and V are really perpendicular to each other, then only VBA by C. So with this, BIA is the IMF magnetic field, and the magnetic field variation is known as 1 by R square and 1 by R, both I directions and R directions. And if you do that, EP by EE can be 1 by R. So these are simple scaling laws. Solar energy input is given by WP and IdP square, that is the circle that makes with the radius dp, and the other things that magnetic energy d squared by 8 pi flux, then you get the velocity, and then velocity is c e by b. So that is the flux that you get from the sun or any planet, and if you know or art, and if you find out the ratio, that is given by 1 mp by me, 2 by 2/3 and r over minus 4 by 3. Now look, all this depends upon the magnetic moment of the planet and the distance r. So, and of course, you have to know the corresponding energy of the, in the case of art, corresponding electric field in the case of art, and then you can find everything. But this is the scaling laws. Now, however, and I think I spent a few minutes for this, which is of probably not very important nowadays, but it goes into the history because of the fact that is how we started doing the magnetosphere of outer planets. Nowadays, you have got a lot of observation from the satellite, so automatically you can, or immediately you can get values for all these parameters. Anyway, let's start with the magnetosphere of Jupiter. Jupiter has a strong magnetic field. It is rapidly rotated planet, and if you use the scaling laws, the distance of the magnetic poles of the Jupiter is around 45 RJ. But however, the observations of Pioneer 10, this was found to be in range of 50 to 100 RJ. There's a lot of difference. Well, the one of course 45 is nearer to 50, but it goes beyond that to 100 RJ. So the scaling laws does not seem to satisfy the parameters that you obtain by the observations of Pioneer 10. Now, could that be because of rapid rotation, which is not there in the case of art, or could be something else? We'll see that. Dipole could be rotating near the surface because of the rotation, but it can break down near a critical distance where the rapid rotation, which gives you the centrifugal force, and that force may be large, such that cannot be contained by the magnetic field or magnetic field tension. It can go out. So the radial flow model is then proposed by Canal and Coronati first, which says that beyond the critical point, which is given by rho v square is equal to v square by 4 pi, rho v square is not the um, solar wind dynamic pressure in this case, it is the velocity which is associated with the rotation of the plasma, rotation of the planet, which gives rise to centrifugal force, and that is associated with this pressure rho v square. And if that is equal to the tension which is given by the magnetic field, then beyond that the plasma cannot be contained by the magnetic field. So there would be a radial flow model of magnetosphere in the case of Jupiter. So there is a picture I can show there that is indicates of the because of the fact that there is a rotation and you have a centrifugal force, and that would try to take away the plasma away from it, from the center, but there is a magnetic field. Magnetic field is a pressure as well as tension, and that wanted to keep this plasma inside, but unfortunately it cannot do, because beyond a certain point the plasma pressure becomes large, because the magnetic field away from certain point decreases, and therefore the tension decreases or the magnetic pressure decreases, and therefore he cannot contain the plasma inside, and therefore there would be a radial flow beyond a certain critical distance, and that critical distance in this case called Alban radius. That is because of the fact it is associated with the Alban velocity. That means v square is equal to v square by 4 pi rho, and that's where the breakdown of this motion comes. So there is an outflow planetary wind beyond this radius. So you can now have a kind of planetary wind. But you can ask whether reconnection can still be important. I think so. If we go away, the magnetic field configuration does not completely change at the subsolar point, and therefore there could be reconnection taking place, and when there is a reconnection, then the plasma behavior would be similar to that of the Earth. So therefore there would be tail on the other side of the magnetosphere, then which will produce the convection. But however, there exist outflows due to some other processes inside the magnetosphere of Jupiter. You see, the magnetosphere of Jupiter is quite complex, will come slowly. Apart from this is very general description that you have a rotation, and because of the rotation, there is a rotational energy, and when rotational energy is large compared to the energy associated with the magnetic field, then there is a planetary wind. But this is the more general case. In addition to that, there are several processes that are happening inside the magnetosphere of Jupiter, which would allow the plasma to flow out from the magnetosphere of Jupiter. And yet, to start with, rotational force produces disk of the current, and thus disk type magnetosphere is okay. This is already obvious there that there is a disk type magnetosphere which can be seen, and there is a current flow which is coming out of the our screen towards us, out of the screen. So there will be current which will be coming out of the screen, and that's the large current. And that is the associated with the disk. We call it a disk current. So let's see next one. What we see is this. The Jovian magnetosphere can be divided in three different regions. One is the inner region, which is less than 10 RZ. Well, 10 RZ actually associated with the beta value of the plasma. The plasma beta is the ratio between the plasma energy and magnetic energy. Inner, inside the magnetic energy is large with plasma energy, by therefore the plasma is confined as you know, and beta is small. But as you go to the other region, away from 10 RZ, that is the middle region, between 10 and 20 RZ, the beta is slowly going from the smaller value to larger value and can be even greater than 1 after a certain distance. So if that happens, then the what happens? Again, I'm saying the same thing, that the omega square r, which is essentially give rise to energy associated with, or you can get centrifugal force, which would be greater than the gradient of plasma in the inside the magnetosphere. Then these two forces are then competing each other when the beta values getting smaller, then this breaks down and therefore plasma lags behind the rotational energy. Rotation takes over then the plasma rotation. So therefore you get beyond RJ the centrifugal force, plasma force and solar wind force or solar wind induced force, they become comparable beyond certain distance. So there will be competitive between these forces, and whichever becomes large would control the plasma. So that is there. But there are several things inside the magnetosphere of Jupiter. One is Io, is a moon situated around 6 RJ, and that is the major source of plasma for the magnetosphere of Jupiter. What is it? This is a moon which is quite active, and it produces volcanically quite active, and it gives rise to a lot of sulfur dioxide material from inside, and then magnetosphere of Jupiter are loaded with this. So, and since this plasma is rotating at that region, because still radiant plasma pressure is large, so rotation still exists. Therefore, a plasma from the IO, which IO goes around, and therefore it produces a torus around the magnetosphere, around the Jupiter in the magnetosphere. So you get a plasma torus associated with the moon Io. Then it has a lot of influence. What are the influences? One can say is that one of them is very simple, is that it is cold plasma it produces inside the magnetosphere, and there are plasma outside which is hot on the other side, or toward in the side tailward side of the magnetosphere. So there could be some interaction between the plasma associated with the torus and the plasma associated with the outside magnetosphere. What is it? You have a There is a boundary you can think of. In a boundary, there is a dense cool plasma and a light hot plasma on the other side. So the plasma sort of uh, having a density gradient, and since there is a density gradient with the associated reflexivity of the magnetic field, therefore it will produce a kind of instability. In this case, we call it a interchange instability, plasma interchange instability that is taking place at the boundary. Now, it is similar to, this instability is similar to relator instability, because in relators you get you have gradient and plus the gravity. Now here the gravity is replaced by the force associated with the motion along the magnetic field of the plasma, which is actually the force. We can call it the centrifugal force, if you like, or similar to centrifugal force, because it is associated with the plasma motion around the magnetic field, which is circular in nature. So this, then what happens, that the plasma can be transported across the surface like we have in the case of spreader. The plasma from the heavier region or denser region can move to the plasma the lighter region, as in the case of the um, um, relator instability in the spreader. There actually, here you can see even in the other direction, that the plasma from the outer region can go inside the magnetosphere. So there can be a plasma transport from outside, that is the hot plasma, across the surface and can go in. And in the cold plasma from inside or from the torus can go out. That is because of the fact that there is a relator type instability, or we can call it um, fluxative interchange instability. So this is one way by which you can have the plasma transport across the magnetic field. Okay. So that is what it is written, that iogenic plasma enclosed in the magnetic bubble breaks off to inject plasma into the magnetosphere. So one part of the plasma goes out, the other, the buoyant magneto flux, which is buoyant because that is less in the density, which can come inside. So that is an exchange of plasma across the boundary. I've said several times. Now next, see what we have. There is something else can happen. In the case of the magnetosphere of Jupiter, there is therefore, you can see there is a plasma flow coming out, whether you can call it a planetary wind or whatever. It is coming out because of the rotation away from the center of the earth, and the motion of this plasma can be seen in this picture by giving number 1, 2, 3, 4. in the left-hand side of the picture. When the plasma goes out in that direction, it then carries the magnetic field with it, and this is in the left-hand side picture is in the equatorial plane, and right-hand picture is the meridian surface. They are perpendicular to each other. So if you see number one, that the particles are coming out from the center of the planet, and it carries the magnetic field with it, and when it carries the magnetic field with it, it gives a picture as shown on the right hand side, number one. As it goes on, then the magnetic field is still stressed, and when it is stressed, then in one of the closed magnetic field lines can see a neutral point. When it sees the neutral point, then it can then produce, go furthermore, there could be now one X-type neutral point which is shown by the card, by this arrow there, and there is a circle on the other side where there could be a neutral point which is O-type neutral point. That means inside the circle there would be magnetic field which would be zero. There would be another neutral point which is O-type neutral point on the third picture. So there would be O-type neutral point there, and then there are kind of reconnection that is going to take place. And if the reconnection takes place in one side, that the plasma island or plasma magnetic island or plasmoid can be detached from the magnetosphere and it can go away. Where on the other side, there is a lot of plasma flow at the reconnection going towards the magnetosphere of Jupiter. So this is a kind of picture which can be associated with the reconnection that can take place because of the plasma flow, which is which is a peculiar picture, peculiar things about of the magnetosphere of Jupiter. So there is now another way of explaining iogenic plasma flow, outflow, and inward transport of hot plasma. So this is the another picture by which you can describe the same thing. And interestingly, these are observed by the satellite that there exists the kind of plasma that you can expect from these reactions. Either in the case of the flux tube, either in the case of what we call the flux interchange instabilities, or in the case of reconnection. Those people who believe in reconnection much more than the other one, they would certainly give enough weight to these aspects of the plasma motions. So this is a kind of um, plasma motions in the case of magnetosphere of Jupiter. I think I'm spending a lot of time. Anyway, let's see next what we can see. Oh, what did I write? See, let me see whether that exists in my lecture. Oh, there is something called this kind of cycle that we have here. This is known as the Bacillinius cycle of magnetic reconnection, which is similar to the Danze cycle which was there in the case of the magnetosphere of the Earth. I forgot to mention that, that's why. Now next point that I want to talk is that there are three important, apart from the Io, there are two important moons of Jupiter. One of them is Ganymede, and the other one is Europa. Ganymede is totally locked because its one side is always facing the Jupiter. And you can find out some other moon also doing the same thing. It is interesting for the case of the Ganymede because it has magnetic field. That's the only planet and only moon that we so far know that has magnetic field, which is then generated by the some convection in the core yes, and that core has the fluid which is iron rich. In the case of Jupiter, this is not iron rich, metallic hydrogen. In the case of this, it is the iron rich, same as that of the Earth. I don't have the picture for that, so I'm having the same picture on the screen. It has the dynamite has an oxygen atmosphere. Voyager 1 and 2 has the measurement of its size. Galileo experiment measured the magnetic field, so it becomes Jupiter of Jupiters. That's what they call it. Interaction with Jupiter with this moon is something very interesting. It is similar to that of the interaction between the solar wind with magnetic field of the Earth. But there is one difference. The rotational velocity that is interfaces with the magnetic field of this planet, that velocity is not supersonic. That is the subsonic velocity. And since it is subsonic velocity, it does not produce any shock. There is no shock in front of this moon, although it has a magnetic field, and although it is interacting with the plasma motion from the magnetic field from the magnetosphere of Jupiter. So that is what is the difference. And magnetic field is a dipole tilted with respect to the rotational axis, and it is almost 176 degree directed against Jovian magnetic moment. So that is interestingly there is a process like this. Then the 3D configurations. That the magnetic field of the planet of the moon is associated with the picture that is shown. There are open field lines because of the reconnection, one on its outward and the other one is in outward. Side, and this is a kind of picture that it had because of the reconnection of the magnetosphere of Jupiter with that of moon. So that's an interesting part of the magnetic, and a lot of other things is of course could be associated like the aurora in the planet, aurora of the moon. So we have aurora in aurora, and so on and so forth. A lot of things can happen. But there are conjunction of three planets. I can see that every rotation of the dynamite, this moon goes twice, and the Europa goes 4 times. So that is the sequence they take in their motion. And there are certain times there some interesting interaction can take place between these three um, moons of the planet Jupiter. This is the same thing. We are saying how this interaction takes place from the left to the right, because the plasma is coming from the right to the left, because it is moving in the rotational direction. And plasma, of course, the direction of the magnetic field would be suitable at a certain point for the reconnection, and that's how it happens. It is not the same as that of the Earth, because the plasma motion is rotational plasma motion, rotational velocity, and sees magnetic field coming perpendicular to it, and sometimes it can get in such a way that there could be reconnection of the magnetic field. So that's the situation of the magnetic field, Jupiter's magnetosphere. There's something more left of the Jupiter's magnetosphere. Benita,
Oh, sir.
now that I won't be able to finish this,
Okay, sir.
shall I continue or will stop?
Because they got next
Okay.
class. So
Then I'll have to do
we'll
it.
have to stop for today. Tomorrow we can
Huh?
continue. Tomorrow, কাইলে কৰিব লাগিব আৰু sir. কাৰণ সিহঁতৰ এতিয়া ক্লাছ থাকিব নেক্সট ক্লাছটো।
কাইলৈ কৰিব লাগিব নহয় এই জুপিটাৰ মই বহুত সময় খৰচ কৰিলোঁ।
ক্লাছ নাই।
তোমালোকৰ লাভ হ'ল নে নাই নাজানো, কিন্তু খৰচ কৰিলোঁ বহুত সময়।
নাই একো নাই ছাৰ।
এতিয়াও বহুত বাকী আছে, 3টামান আছে।
সেইটোৱে কাইলে ছাৰ ইহঁতৰ মানে 10:30 পৰা পিছৰ ক্লাছটো নাথাকে আৰু থাৰ্ড ক্লাছ, সেইকাৰণে কাইলে অকণমান দেৰিলৈকেও কৰিব পৰা যাব। আজি খালি এতিয়া ইহঁতৰ ক্লাছ আছে, সেইটোৱে।
গতিকে আজি বন্ধ কৰোঁ নেকি?
অ'কে, য়েছ ছাৰ, য়েছ।
তেনেহ'লে কাইলৈ 8:30 নহয়?
কাইলৈ 10:30, হয় একেই, হয়।
Okay.
Okay, sir. Thank you, sir.
Thank you. Question থাকিলে কাইলৈ সুধিবনে আজি?
কাইলৈ সুধক নেকি? কাৰণ
সিহঁতৰ ক্লাছ আছে। কাইলৈ মই টাইম অলপ এৰিম, কুৱেশ্যন দিব পাৰিব।
হয়, কাইলৈ সিহঁত ফ্ৰী থাকিব থাৰ্ড ক্লাছটো, তেতিয়া ডিছকাছ কৰি ল'ব পাৰিব নেক্সট যিমান আছে আগৰো মিলাই পেলাই। ঠিক আছে ছাৰ, তেতিয়াহ'লে
থওঁ আৰু।
হয় ছাৰ, বাই।